Welcome to Ask and Learn.
We want to sketch a graph of y is equal to 2 plus 3x squared minus x cubed. Now, in the chapter, we're given a laundry list of things we should do when we are trying to go about graphing any kind of function. So the first thing they tell us is we should figure out what our domain should be. Well, since this is a polynomial, we know polynomials have a domain of all real numbers, which is the same thing as just infinity to negative infinity to infinity. The next thing they suggest we find is our intercepts. So let's go ahead and find our y-intercept first. So our y-intercept is when x is equal to 0. So we get f of 0 is equal to, well, the x squared and the x cubed term go away, and we're just left with 2. So we get our y-intercept to be 2. And now for the x-intercept, we let y equal to 0. And I'm going to be completely honest and say I have absolutely no idea how to go about solving this without using some kind of calculator or doing things that are not worth our time. But if we do the rest of the things in this problem, we will be able to figure out where our x-intercepts should be and how many we should have. So it won't be too big of an issue that, at least right now, we have no idea what this value or values of x should be. The third step is to find symmetry. So this is to look at what f of negative x is. So plug it in f of negative x, we'd get 2. The square would cancel that negative out, so we just get 3x squared, and then the cube will make it negative, so we get plus 3x cubed. Oh, not plus 3x, but just plus x cubed. Now, this does not equal to f of x, nor does it equal to negative f of x. So this tells us no symmetry. All right. So we've gone through the first 3 steps. The next part is to look for asymptotes. And we know that this here will have no asymptotes with it just being a polynomial. But we can at least use this to help us find our end behavior. So let's go ahead and check what the limit as x approaches infinity of f of x is going to be. And I keep saying f of x, which is just supposed to be our y over here. So this is our f of x, if it wasn't clear. So it's a cubic function. So we don't really need to care about the rest of the terms then. And since it has a negative coefficient and it's odd, then as x goes to infinity, this should go to negative infinity. And likewise, when this goes to negative infinity, well, since it's an odd function, or since it's a cubic function, if positive infinity goes to infinity, then this one should go to the opposite. So as x goes to infinity, our end behavior goes to negative infinity, and as x goes to negative infinity, our end behavior goes to positive infinity. All right, so we got the asymptotes, or at least our end behavior, not really asymptotes. Now we want to find intervals of where this function is increasing / decreasing. So that means we want to look at what y prime is. So y prime is going to equal to, so the derivative with respect to x of that polynomial there. So 2 plus 3x squared minus x cubed. And to take the derivative of those, we would just go ahead and use power rule. So derivative of a constant would be 0. The derivative of 3x squared, well, that's going to be 6x, and then we subtract 1 from the power, so we'll just have a power of 1 now. And then power rule on x cubed will be pull the 3 out front, and then subtract 1 from the power, and we get x squared. So let's go ahead and factor this. So I can factor out a 3x. And doing that, I'd get x minus, or 2 minus x. And since this is a quadratic with a negative leading coefficient, we know it should look something kind of like that there. So here we have x is equal to 0. So if I set that equal to 0, we have x is equal to 0 and x is equal to 2. And the reason why we care about this, let me go ahead and zoom out a little, is we know that y prime will be strictly greater than 0 or increasing on the interval. So it would be from 0 to 2. So 0 to 2. And then y prime will be strictly less than 0 on the rest. So negative infinity to 0, union 0 to infinity. All right. Next, we want to find our local maxes and our local mins. So local max slash min. And we already did part of the job because we know x is equal to 0 and x is equal to 2 will be possible local max or local mins, at least there are critical points. So we can use the first derivative test to tell us whether these will be mins or maxes. So before we get to 0, so from negative infinity to 0, the function is decreasing. So to the left of x is equal to 0, the function is decreasing. And then on 0 to 2, the function is increasing. So this tells us x is equal to 0 will be a minimum. Then for x is equal to 2, so on 0 to 2, we said this is increasing. And then from 2 to infinity, oh, so actually I caught a little error down here. This should actually be 2 to infinity. I'm glad I caught that. And so then on the other side of 2, it's decreasing like that. So this at x is equal to 2 would be a max. So we have our max and our min. And now we want to look at our concavity. So concavity slash inflection points. So we're going to need to look at y double prime. And we already found that y prime is this. And to take the derivative of 6x minus 3x squared, we're also going to need to use power rule again. So d by dx of 6x minus 3x squared. So the derivative of 6x would just be 6. The derivative of 3x squared, well, we move the 2 out front. So it would be 6x, and then subtract 1 from the power of 2, and we just get 1. All right. Now, we know that this here is a line that is decreasing. So wherever we find what makes this equal to 0, we know it will be an inflection point, since to the left it will be positive, and to the right of that point it will be negative. So let's just go ahead and factor that 6 out really quickly, get 1 minus x. So now if we set that equal to 0, that implies x is equal to 1. And maybe we'll just go ahead and use this to tell us where it's concave up and concave down. All right, so y double prime will be greater than 0. And so remember, this is concave up. So concave up. Well, that will be to the left of our point of inflection just by looking at what 6 minus 6x looks like. So this would be on negative infinity to 1. And then it's going to be concave down on the rest of the interval. So 1 to infinity. All right, so now we have all the information we really need to sketch this graph. So let's go ahead and plot our y-intercept. So we know that's supposed to be at 0, 2. And then we also have no idea where our values for the x-intercepts are supposed to be. But using our asymptote information or our end behavior, we know that on the left, this function is increasing, and on the right, the function is decreasing. So something we should probably also find out is what values our local max and our local min are supposed to be. But we actually don't even need to do that, because since x equals to 0 should be a min, it should curve out like this at this point there, and at x is equal to 2, it should come up like that. So from this, we can tell that there should be no x-intercepts to the left of 0, so we can just go ahead and connect. Let me go ahead and draw that maybe a little bit better. We can just go ahead and connect. Oh, I guess it's not going to want me to do that, so let me just erase instead. Right. So it'll look something kind of like, oops, wrong color. Let me go ahead and draw the green. So it'll look like that. And then we know it's going to have to connect up here at 2. And then after this point, since there's no more local mins or local maxes, we know it just needs to keep on going out until the end. So this here would be a nice little sketch of the graph. You could go back in and figure out what this actual value here is. But for the most part, since we're just trying to sketch it, I would say this is sufficient.